Chapter 5, Number 28. A shopper pushes a 7.5 kilogram shopping cart up a 13-degree incline as shown in the figure to the right. Find the magnitude of the horizontal force F needed to give the cart an acceleration of 1.14 meters per second squared. So this gets complicated because there are a lot of forces going on, and yet none of them really point in the same directions. So let's do a quick sketch. I don't really like that. Let's do, this is her somewhat steeper thing, and I'm going to draw this instead. I say, what forces act on this cart? Well, we definitely have the thing we're looking for, F, which points directly horizontally. And then we have the weight, which points directly down. But then it gets a little interesting, because we also have a force from the floor on the cart, and that points perpendicular to the floor. So not straight down, but at some angle perpendicular to the floor. And finally, the thing accelerates, but it accelerates up the incline, not over to the right entirely, but also somewhat up. These sort of tilted problems are by far the worst that you can see in Newtonian dynamics. We need to have an intelligent choice of axis, and we're going to have to resolve some of our forces. They won't lie along our axis. Now, our traditional axis is, of course, usually something like vertical and horizontal. But that's not the axis I'm going to choose. I'm going to choose an axis which is parallel to the incline, and I'm going to call that x. And the reason I do that is because then my acceleration lies entirely along that axis, and that will make life a little easier later on. And then perpendicular to that, we have, I will put y, just because I always want a perpendicular one. That gives me some weirdnesses, all right? So because, I guess I should have named this other guy. Sorry, the normal force is that one. And then what we can do is that our normal force points directly along our y-axis, so that will be easy. But our applied force F and our weight force F sub g do not, so I need to resolve them. So I need to say, here is force F, and then I'm going to break it into parts. So I'm going to break it into something which is along my incline, parallel to my incline, and that's going to be F sub x. And I have another part that's going to be perpendicular to that, and that's going to be F sub y. But these are no longer really horizontal and vertical, and that's the thing that's kind of weird. And then, happily, I know that this angle is theta. So I'll be able to resolve those. Before I go on and do that, though, I'm going to do the gravitational force, because that one's also going to be kind of strange. And the gravitational force has a part that goes down the incline. I'm going to call that FGX, because my gravitational force is FG. And then another point that goes into the incline, trying to push it through the ramp, and that's going to be FGY. And our tricky bit is, what is the angle of that? So, kind of going off to the side now, just for ease, I'm going to make this a much larger thing. So I'm going to say, here is FG, and FG has a thing which points along our incline, and a thing that points perpendicular to our incline. So that's what we're looking at. Trim that out a little nicely. And remember that, of course, this is a right angle. And now I'm going to sort of superpose the incline itself, making it as long as I need. And I'm going to remember that this angle here was theta. But if that angle is theta, then this angle is 90 degrees minus theta, because of this right angle. And that in turn says that this angle, let's call that angle for the moment. Sorry, let's go back and name this angle phi. Then this angle is 90 minus phi because of this right angle. So this guy here is 90 minus phi. I'm going to call that for the moment alpha. And I say, well, alpha is 90 minus phi, but that's 90 minus theta, which is 90 minus 90 plus theta, or just theta. Bizarrely enough, maybe, this angle is the same as that angle. And it has to be by the geometry. So I can go back to this and say that I actually have that picture where this is my right angle. Just like here, I had the other picture and that was my right angle. So the measurement of theta has flipped. It was measured from the horizontal, but for gravity, it's as if it's measured from the vertical. This happens a lot in tilted axis problems, so you should feel familiar with it, but it might not be a thing that you know offhand. So I'm going to go back and move on to get rid of these scribblings and kind of, now that we've got that, just redraw our triangles nicely. All right, so now we can get our various components in terms of our various guys. Now, I don't know F. I even don't really know FG, although I can compute it, but I can still get rid of Fx and Fy in terms of F or Fg, which hopefully are things I would know. So for instance, I go to this first triangle and I say that the sine of theta is the opposite divided by the hypotenuse. So for us, that's Fy over F, which I can turn around and say that means that Fy must be F sine theta. And likewise, for that same triangle, we would have the cosine of theta is the adjacent side over the hypotenuse. So Fx over F, or Fx has to be F cosine theta, which is not a surprise. Once we find one of them, we know the other one's going to be the other trig function. So that's all kind of relatively traditional in what we've done before. It's going to be the same thing, but look a little stranger here when I say, well, in the green triangle, the sine of theta is the opposite side over the hypotenuse. But now the opposite side is Fgx, and the hypotenuse is Fg. So that tells us that Fgx equals Fg sine theta. And then likewise, the cosine of theta is going to be the adjacent side divided by the hypotenuse. So that's going to be Fgy over Fg. And so Fgy, sorry, it doesn't look, that kind of came out pretty badly in the writing. Let's try that again. Fgy is Fg cos theta. And we should note that we've had sort of a reversal here, where here we have x associated with cosine, and here x associated with sine. The reason is that in this triangle, the angle is drawn relative to the horizontal, so x is associated with cosine. And here, the angle is drawn relative to the vertical, so y is associated with cosine. Not a big deal, just kind of out there. So that's been a lot of trig, and doesn't seem like it's paid off at all. But what's going to allow us to do is take our free body diagram and now rebuild it with things that are either parallel to or perpendicular to the axis that we've picked, which remember is x and y. So, for instance, we still have the acceleration going straight up the incline. So it is parallel to our chosen x direction. And then we have, for instance, we've broken f into these two components, so I'm going to replace f with those two components. So there'll be fx pointing up the incline, and then fy pointing into the incline. And then I'm going to do a little color rearrangement a little bit in the original figure. So I'm going to turn this guy green like we've been doing. And I'm going to turn Fn to a different color as well. So this is not a big deal, but just I'm not changing anything on the figure. I just want to be consistent with our later colors. So this is Fg. And then Fn points into or out of the incline, which allows me to say right away it's still pointing along our y-axis, so Fn I can just draw like that. And then our final thing is that we have Fg, and it's got a component down the incline and a component into the incline. So when I do that, I have an Fgy pointing that way and an Fgx pointing down the incline, which seems to have made it even more complicated because I've invented new vectors. But now life gets relatively easy because I know that in each direction, the sum of the forces in that direction has to be the mass times the acceleration in that direction. So for instance, in the x direction, we would have that, but in the y direction, independently, we would have this. This is, of course, just Newton's second law. But I can also say from before, I can look at the diagram and I can say, oh, sigma Fx, the net force in the x, based solely on the diagram now, must also equal, well, there's an Fx that points in that direction, and there's an Fgx, but it points in the opposite direction. In the same way, sigma Fy is only the forces that point along or oppose the y-axis, which would be this one and this one and this one. And so we see that we have Fn pointing out of the incline. There's an Fgy, but it points into the incline. And there's an Fy, but it also points into the incline. And the signs here again just reflecting that they point opposite to the direction that I picked as plus y. The next step then is to just put these things together. The thing from Newton's second law versus the thing from the free body diagram. And that's not unusual for Newton's law problems, where you'll set up your free body diagram, you'll get your forces from that, and then you'll connect them using second law. So that's all we have to do next, which will happen on the next screen. So now, believe it or not, all we have to end up doing is substituting in. So we'd have something like Fx minus Fgx equals ma, and Fn minus Fgy minus Fy equals 0, because the cart accelerates along the incline, but doesn't accelerate out of the incline. And we can do one better than that, because we have these things for Fx and so on. So we can say that we have F cosine theta minus mg sine theta equals ma, and we have Fn minus mg cosine theta minus F sine theta is 0. And remember a couple of things. I have replaced Fg with m times g, and then I've replaced Fgx with Fg times sine, and so on from a couple screens ago. These equations are both true, and they're independently true, so I can use either one of them to solve the problem. I am going to end up using this one, because in it, there's the thing I'm looking for, and then there's stuff I know. I have the angle, so I know the cosine. I have the mass, so I know m and g, and I was given a. In principle, the second equation is also true, and I could use it, but it ends up with two things I don't have. I don't have the f that I'm looking for, but I also don't have any limit on this Fn, and so I can't do anything with it. This equation would give me only stuff in terms of this unknown Fn, and that's not sufficient to solve the problem. So I'm going to go back and use the first one. So we have F cosine theta minus mg sine theta equals ma. You could plug numbers in here and solve it. I am sort of algebraically obsessed, so I'm going to solve it over and then put the numbers in. So I'm left with, at that point, we're left with F cosine theta equals ma plus mg sine of theta. And then I'll divide by cosine of theta to get that F equals ma plus mg sine theta over cosine of theta. So now we just start plugging in some numbers. We have a 7.5 kilogram mass times an acceleration of 1.41 meters per second squared. We have the same 7.5 kilogram mass now times the free fall acceleration constant of 9.81 times the sine of 13 degrees, all over the cosine of 13 degrees, which is complicated on your calculator, but not impossible. The final answer comes out to be 27.8 newtons. So we'd have to push horizontally at that rate, at that force, to cause the described motion to occur.